Hello class, today we are going to be implicitly differentiating, but we're going to start off with just taking a basic derivative and reviewing some notation. So one way that you could find the derivative of y, we could call that y prime. But another notation for y prime is dy dx. And that is the notation we're going to be focusing on today so that we will be able to implicitly differentiate. Okay, so those two mean the same thing, but taking a closer look, the way that you say that is you are taking the derivative of y with respect to x. You need to remember that whatever variable is in the denominator, that is what you're taking the derivative with respect to, and whatever variable is in the numerator is what you are deriving. So silly story I've made up to try to help you remember which one is which. So if you use your imagination for a moment, picture that that is a road that you are deriving on. Okay, so in the numerator, that's where I have my car, because on top of the road, you would be deriving. So we're deriving y, and then with respect to x. So again, using your imagination, we're like, what goes below the road, or what gets buried underneath the ground? That is the dead. Ugh. So we respect the dead. So we are deriving the y with respect to x. Hopefully that's just a quick trick to help you remember which one's which. Deriving, respecting. Taking that one step further, because sometimes you will not see a variable in the numerator. You will sometimes see like d over dx, and that would mean that you are taking the derivative of any variable that is not an x, you are deriving, and then what the variable is in the denominator is with respect to x. I'm not going to say too much more about that until we have some examples, because those are going to be a little ways down the road. Okay, so here we go. Find dy dx of y to the third power. Now, if I define y, that's really not that tricky. We've done this. I could replace the y with that x squared minus 9, and then you'd say, hey, this is something to the third power, something more than plain x. That would be an input function, the ugly, and so I'm going to need the chain rule. So I would move the 3 to the front, have x squared minus 9, subtract 1 off the exponent, getting to the second, and chain on the derivative of x squared minus 9, which happens to be 2x. I could put it all together, and my final answer would be 6x times x squared minus 9 to the second power. Nobody go distribute the 6x through, right? Exponents come before multiplication, so that would be our final form. But what if I did not know what y represented? Well, if I don't know, it could be more than x, right? It's an input function. So really specifically, see how that denominator has an x? When you look at what you're taking the derivative of, if it is not the variable in the denominator, so it is not x, it is going to require the chain rule if the exponent is higher than 1, or maybe we have a trig function or something else going on. Okay, so that y is our ugly to the third power. So we're going to have 3 ugly to the second, chain on the derivative of ugly, of that input function. Now the derivative of y prime, like if my function was called f of x, and I said, what's the derivative? You'd say f prime of x, right? That is not 1, so it's going to be y prime. So my final answer there is 3y squared y prime. Okay, so let's take a look at several more. Dy dx. Notice every one of these terms over here that we're going to take the derivative of, they have an x. Well, that's good. See how the denominator dx with respect to x. So the derivative of 5, everything's normal. Derivative of a constant, 0. Derivative of x, 1. Derivative of 3x, 3. The derivative of 8x squared, 16x. The derivative of 2/3 x to the third, that 3 moving to the front times 2/3, right? The 3's cancel and we get 2. Subtract 1 off the exponent. We get 2x squared. We have memorized trig derivatives, and the derivative of sine x is cosine x. Okay, next, what if our variable is not an x? Specifically, it is not the variable in the denominator. So we're going to have to treat whatever is not an x like an input function. So we're going to always chain on the derivative of that input function. Okay, but when it's plain y, think about y is like g of x. If I said find the derivative of g of x, you'd say g prime of x. So the derivative of y is just y prime. Okay, then 3y. Not much different because we do have two things multiplied together, but that 3 is just a constant multiplier. So we kind of set that off to the side and think, what's the derivative of y? And the derivative of y there would be y prime. And then the 3 comes back with it, so we're going to have 3y prime. You're like, okay, it doesn't look much different. Okay, how about 8y to the second? That y is an input function, so we have to use the chain rule. So the 2 moves to the front, 2 times 8 is 16, y to the first power, chain on the derivative of y, so y prime. And then the final answer there would be 16y, y prime. Okay, how about 2/3 y to the third? That y is something other than plain x, so we're going to have to chain on the derivative of y. So 3 moves to the front, so 3 times 2/3, y to the second power, chain on the derivative of y. If we simplify, we end up with 2y squared y prime. Okay, here's another one. How about we have the sine of y? If it was plain sine x, then the derivative would have been cosine x. But because we have the sine of an input function, it's going to be cosine of that input function, chain on the derivative of, in this case, y, so y prime. Now, I cannot leave it like this because you want to just be really careful, because when you have a trig function followed by things that are multiplied, they attach together. So this makes it look like you have cosine of y times y prime, and those are not stuck together. So your final answer, you would maybe want to write y prime cosine of y, or maybe put cosine of y inside of parentheses, but just make sure those stay apart so that it's really clear. We're going to continue to get more involved, a little trickier problems. So here we go. This time we want to find dy dx. We want to find the derivative with respect to x. We have sine x times tangent y. So we are going to have to use the product rule because we have two things multiplied together. So if I just apply the product rule to begin with, we're going to have the sine of x times the tangent of y's derivative plus the tangent of y plus the sine of x's derivative. Let's tackle the derivative of tangent of y. Now, if this was just tangent of x, the memorized derivative of tangent of x is secant squared of x. But because it's the tangent of an input function, we have to chain on the derivative of that input function. So this one is going to be secant squared of y, but multiplied by y prime. Okay, then let's tackle this one, the derivative of sine x. Well, that one's just like normal because x, we're good, it's with respect to x. So the derivative of sine x is just cosine x. And I think I'll go ahead and say the chain rule has always been applied. It's just that if I chain on, if I go the derivative of sine x is cosine x times the derivative of x, well, that's just 1. So that's why we don't really think about the chain rule. Okay, bring down those other pieces and we have our final answer. Okay, let's take a look at another one. We have a whole big mess of stuff to the fifth power. So all of that in yellow is the input function. So we're going to be using the chain rule, not just because we see a y, but we have a whole lot of stuff to the fifth power. So applying the chain rule, 5 moves to the front, all that in yellow to the fourth power, chaining on, multiplying by the derivative of what's in yellow. All right, now we need to tackle finding the derivative of x squared times y squared. Okay, first noticing that what we want to take the derivative of, two things multiplied together, so we're going to need the product rule. So setting that up there, we're going to have x squared times the derivative of y squared plus y squared times the derivative of x squared. Okay, next, let's tackle that piece. The y is, see, our denominator is with respect to x. So anything that is not an x, we will need to chain on the derivative of what is not x. So in this case, y. All right, so we're going to have 2y to the first power chain on the derivative of y. So 2y to the first power times y prime. Then tackling x squared, the derivative of x squared, well, that one's normal because it's just an x. So we have 2x to the first power. Okay, bring down a bit here. Let's bring that little piece down. As we simplify that power to a power, multiply. All right, so we have x to the second power to the fourth power. That's going to be x to the eighth and y to the eighth, and we have a times 5. Okay, so we have 5x to the eighth, y to the eighth. Okay, next let's bring down what this was being multiplied by. I probably should have put a set of parentheses up here too, but we have x squared times 2 times y prime. So that is 2x squared y prime. And then on the back half here, we have y squared times 2x. So we have 2 xy squared. Okay, and one more time, just right here, after that multiplication symbol, that really should have been in parentheses. Okay, simplifying, I don't know, you could go either way. You could either factor out more of what's in common and maybe call that simplified. I'm going to go ahead and distribute the 5x to the 8th, y to the 8th through. And my final answer is going to be 10x to the 10th, y to the 9th, y prime, plus 10x to the 9th, y to the 10th. All right. Why are we going to need to implicitly differentiate? There's a few purposes, but the main purpose that we're going to encounter right now is it's going to allow us to find the slope of the tangent line to an equation that you cannot solve for y. What's in front of you is going to have a mix of x's and y's. If you could get y all by itself on one side and then you wanted to take dy dx, you wouldn't need implicit differentiation. So the trigger for you, like what does the problem look like, and you've barely even read the directions thinking, what are they going to ask me to do? Well, if you see an equation where there's x's and y's all mixed together, or there's many, many variables mixed together, you're probably going to be implicitly differentiating. So far, what we've been doing is finding the derivative dy dx, but we've only had a single term. So notice here that we have what's called an implicit function. Let's contrast that with an explicit function. So an explicit function is one where y is all by itself. And we could take the derivative of this explicit function with all those basic rules that we've learned so far. Okay, but this one, notice the equation we have in front of us, we cannot just solve that equation for y. So what we're going to need to do to find dy dx is we're going to have to do what's called an implicit differentiation. Let's tackle each one of these, keeping in mind that y is the ugly, right? It's the input function. And that means that if it is not something that's just x, right? We're going to have to chain on the derivative. All right, let's go ahead and tackle that one first. Y to the 5th power. 5y to the 4th, but because it is not x, because it is with respect to x, because it's not an x, we have to chain on the derivative of y. So the derivative of this first term is 5y to the 4th y prime. Okay, then the next term, that one's easy. Just normal derivative, move the 2 to the front, subtract 1 off the exponent, and we have 6x. Technically, you are taking the derivative of, chaining on the derivative of x, it's just that it's 1. Okay, then equals. Next, we have the derivative of sine x. Again, this is just x. So the derivative of sine x is our memorized cosine x. Okay, next, we want to find the derivative of negative 4y to the 3rd. So because y is that input function, it's the ugly, we have to chain on the derivative of y. So we're going to have 3 to the front, so minus 12, y to the 2nd power, chain on the derivative of y. All right, now if you're wanting to find dy dx, that means you want to find y prime. So ultimately, if you're finding dy dx, you need to get the y prime by itself. So the next thing I want to do is move all the terms that have a y prime on one side and all of the terms that do not have a y prime in it on the other. Okay, so I'm just highlighting here in blue the terms that have a y prime in it. I'm going to move all of those to the left side, and any term that does not have a y prime in it, I'm going to move it to the other side. Okay, so here I'm keeping the 5y to the 4th y prime on the left. I'm adding over, because we had minus 12y squared y prime, so I added it over, and then I'm keeping cosine of x on the right, but to get the 6x over there on the right with it, I'm going to subtract it. Okay, notice I have all the y primes on the same side, and now that we have what we're looking for on the same side, that allows us to factor that out because they are the y prime is in common to all of those terms, right? So I'm taking out a y prime, leaving me with 5y to the 4th, take out a y prime in the second term, leaving me with 12y to the 2nd. The entire right side is the same. Now we have y prime multiplied by this stuff here in parentheses. So to get rid of that 5y to the 4th plus 12y squared, I'm just going to divide both sides by that, and y prime is alone. So we have found the derivative. We have found dy dx. Okay, here's another one. Determine the slope of the tangent to the graph of 3x squared plus y squared to the 2nd power equals 100xy. You know, this is the equation of some function out there. And if we want to find the slope of the tangent, that means we want to find the derivative. So stop and think, what is it about this equation that tells you you are going to have to implicitly differentiate? Okay, what is the giveaway is we have this equation, this big mess of an equation, but the y is not by itself. All right, so we're going to have to implicitly differentiate. Let's start by just notation. So I'm just saying dy dx. I'm taking the derivative of both sides. That is the a little more detailed notation than just putting little prime symbols. Okay, so next, let's focus there on the left-hand side. And we have 3 and a whole bunch of stuff in there to the 2nd power. So everything in yellow is going to need to be chained on times the derivative of what's in yellow because it's not plain x. So let's start there. The 2 move to the front, x squared plus y squared to the 1st power, but we want to chain on the derivative of x squared plus y squared. Okay, we could just put instead, we could just put a little prime symbol. But the reason why I want to emphasize dy dx is because as we take the derivative, anything that is not an x is going to be an input function. So we'll need to use the chain rule. Okay, so I'm just going to leave it with the simple notation there. Okay, equals, equals. And then there on the right-hand side, I'm going to look at that as, instead of 100xy, I want to really focus on the fact that we have multiplication, so I'm going to say 100x multiplied by y. When we take the derivative of that right-hand side, we're going to need to use the product rule. So 100x multiplied by y. So we're going to have 100x multiplied by the derivative of y plus y times the derivative of 100x. I went ahead and just took that derivative. The derivative 100x is 100. Okay, so the right side is done, but we still have a little bit more calculus to do here on the left. So let's focus right there. Okay, the derivative of x squared is 2x. But the derivative of y to the second, we have to use the chain rule. So it's 2y to the first, chain on the derivative of y, so y prime. Okay, now I'm just bringing everything down. On the left-hand side here, okay, we're going to FOIL. So if I FOIL all of that, I'm going to have this, 4 terms here coming in. And then it's still equal to the same thing. All right, now I can move all of the terms with a y prime in it to the same side and anything without a y prime on the other. So I'm going to move all the blue ones there over to the left-hand side. And anything that is not a blue one, anything without a y prime, I'm going to move it over to the right side. Okay, so I'm just adding and subtracting terms to get all the y primes on one side, everything else on the other. Now that I have all of the y prime terms on the same side, I can factor out the y prime. Okay, and then to get y prime all by itself, we're just going to divide by what it's being multiplied by. And there we have the derivative, which is the slope of the tangent to this function at any x value. Okay, now when I go to find it at the coordinate 3, 1, in the past when you found a derivative, the equation you got had at most something with an x in it. But this time the equation that we get that represents the slope of the tangent to the graph at any point has an x and a y in it. So I'm going to need to substitute the 3 in for any x and the 1 in for any y. So if I replace every x and every y with the 3 and the 1 and simplify, I'm going to end up with 13 over 9. Okay, let's say that you were now asked to write the equation of either the tangent line or the normal line. That's a review. And to write the equation of any line, you need a point and you need a slope. So if we were going to go with the tangent line, we would use the point 3, 1 and the slope 13 over 9. And then we could go with point slope form, y minus y sub 1 equals m times x minus x sub 1. And we'd have the equation of the tangent line. If we wanted the normal line, remember that's the perpendicular one. So rather than using 13 over 9 for the slope, we would want the opposite reciprocal. So we would use negative 9 over 13 for our slope and the point 3, 1. Okay, so you will be asked to write the equation of a tangent line or a normal line. But you first have to be able to get to the derivative so that you can substitute that coordinate in. Okay, one more just to make sure. And this time we're taking d squared y over dx squared. Remember, that's like y double prime. So we want to start with finding y prime first. Okay, so I'm going to find dy dx. I'm taking the derivative of both sides. But because it's with respect to x, anything that's not an x is going to be treated like that input function, and we'll need to chain on its derivative. So the derivative of x to the second is 2x But for y squared, that's going to be 2y to the first y prime. Now the derivative of 25 is 0. I have no idea why. It's like you get caught up in focusing on y's versus x's, and I cannot tell you how many tests or homework assignments that you get to the derivative of 25 and you write 25. But you all know the derivative of a constant is 0, so just be careful there. All right, next I'm going to get y prime by itself. So the only term with a y prime in it is 2y y prime, so I'm going to move the 2x to the other side. And then I can divide both sides by 2y because the y prime is being multiplied by both 2 and y. And then I'll simplify. Those 2's can cancel, and there's my y prime. So we have just found dy dx, y prime and dy dx, same thing. Okay, I want to take another derivative to get me to d squared y over dx squared, find y double prime. So let's just start here. Okay, but notice that y prime, we had a fraction, so we have negative x divided by y. That is going to require the quotient rule to take the derivative. Low d high minus high d low over low squared. Okay, denominator times the derivative of the numerator, and the derivative of negative x was negative 1, minus the numerator, which was negative x, times the derivative of the denominator, which is just y prime. Okay, that's another one where when we take the derivative of y, and you're like, oh my gosh, chain rule, chain rule. Okay, only if the exponent is greater than 1. Like if y would have been y to the third, we'd have 3y squared y prime. But if it's just plain y, just like if it was f of x, it'd be f prime of x. Okay, so it's just y prime all over low squared. So the denominator squared is y squared. Okay, then last little bit still, subtleties. You want to have your answer d squared y over dx squared, you want it to be with respect to x. And you don't want your answer to have anything other than x's and y's. And see how we have that y prime in there? We need to get rid of that. So back here, we know y prime can be replaced with negative x and y. So I just substituted in, everything is exactly the same. I just replaced y prime with that negative x over y. Now we have a fraction within a fraction. So to simplify, remember we're going to multiply by that little mini denominator. So we don't like that little y right in there. So I'm going to multiply the entire numerator by y and the entire denominator by y. Okay, when you multiply the numerator by y, it needs to be distributed. So if I have y multiplied by, right there, y times negative 1, that will be negative y squared. And when I multiply y to this, let's go ahead and think about what that is cleaned up. Negative times negative x over y. Negative times negative x over y is negative x squared over y. So if you have negative x squared over y multiplied by y, the y's cancel, and then we end up with just the negative x squared. Okay, and then in the denominator, y times y squared, all over y to the third. Okay, so your final answer for y double prime should only have x's and y's in it. So if you have a y prime in that final answer that your y double prime is equal to, make a substitution to get rid of it and simplify. This is the assignment that goes with this lesson, class, and you are going to have quite a bit of time to get it done because it is very long. So please do not wait until the due date. It's going to be due on Wednesday night. But let's get started right away so you can make sure you have plenty of time to ask questions and get this sucker done. All right. See you later.